So we have methane at standard temperature and pressure, enters an insulated reactor operating at steady state and burns with 100% theoretical air at the standard temperature and pressure. An equilibrium ideal gas mixture of not just CO2 and H2O and nitrogen. I left out nitrogen. Nitrogen goes for the ride with the air, doesn't it? But they have CO, it's like uncombusted carbon with the methane, as well as unused oxygen. So those are the unused parts, or the disassociated parts of CO2. Okay. Determine the temperature of the exiting products. You need to calculate the equilibrium flame temperature. Why equilibrium? Because it's in chemical equilibrium and there's dissociation of CO2. Now, is there any way that they put anything in here like H2 is part of the products or HO is part of the products? They didn't list it. So even though I said H2O could also dissociate, it's not called for to model that in this problem. So don't model it. Only model the dissociation of CO2. If they would have listed, okay, we get some H2 in the products, well then you have to consider it. Also, they didn't list any dissociation of N2, so N2 just goes through the system. After we calculate for part A the equilibrium flame temperature, then compute the composition of the products. So we want the mole fraction of CO2, the mole fraction of carbon monoxide, the mole fraction of oxygen, the mole fraction of water vapor, and the mole fraction of N2. That's what we're asked to solve. How do we approach this problem? Start off with 100% theoretical air combusting with methane. So CH4 with our O2 plus 3.76 N2. And it goes to, and just do it for complete combustion. So it goes to CO2 plus H2O with a 2 there, plus, and then we come back with a 2 here, and we'll have 2 times 3.76 N2. Is that balanced for 100% theoretical air, assuming complete combustion and no dissociation? You like that? Thumbs up? Good, you're all with me? Good, good. So now what we do is we think about these being our reactants and these being the products, but in the products modify that right-hand side to account for some dissociation of CO2. Well, how does CO2 dissociate? Come up here and remind ourselves that CO2 dissociates by this equation, carbon monoxide and 1/2 O2. That's equation, it's in our tables. We can get the K value, the equilibrium constant for that equation, right? And that's why it's an equilibrium. It's chemical equilibrium. True? So what we do is we leave the right-hand side alone, CH4 plus 2O2 plus, I'll write it a little different. I'll write it as 7.52 N2s. It's a little cleaner to do coefficients in front of each term. And then we'll have the CO2. And I'm going to think about, I started with 1, but if I have so much dissociating, that's what I'm left with. So what is Z? Z is some amount of CO2 that dissociates. So it's the amount of CO2 that dissociates. Okay? So that's why on the right-hand side for the products, we have 1 minus Z. Now we're going to come over here. If Z is the amount of CO2 that dissociates, it's going to produce some CO. But what coefficient goes in front of that CO? Z. Now that was hard. Now the really hard one. You have O2. What coefficient goes in front of the O2? Half Z. You see that? That's complicated, right? Because it's like Z is the extent of the dissociation of CO2. If Z is 0, I have no O2. If Z is 0, I have no CO. Let's say Z is 1. If Z is 1, I have no CO2. It all dissociated. And then I'll have 1 CO, but only a half of O2. Got it? Maybe some of you are like, hey, this is so easy. So this was the hard part. We still have the 2 H2Os going along because the hydrogens need to balance. And we still have the 7.52 nitrogens going along. Now we're ready to write down our equilibrium equation, our chemical equilibrium equation. I write it something like this because I'm going to do, for the equilibrium frame temperature, it has to be in chemical equilibrium as well as satisfy the energy balance. So there's 2 equations that are going to come into play. But let's just get the first one. It's our chemical equilibrium equation that deals with the composition. So what happens is we have K. It's a function of T. It's equal to, and then I look over here and I have the number of moles of CO raised to the power 1 times the number of moles of O2 raised to the 1/2 power divided by the number of moles of CO2 raised to the 1 power. Then I have the pressure divided by 1 atm divided by the total number of moles in my gas mixture. Then I have it to the 1 plus 1/2 minus 1 power. I just applied our equilibrium equation we've done before. Did I go too fast? Did I lose you? Or are you on track? Thumbs up if you're on track. Now we have to adapt it. For our particular problem, the number of moles of CO is Z. The number of moles of O2 is Z over 2. Then we still have to put that to the stoichiometric coefficient in front of this dissociation reaction, which is a half. And the number of moles of CO2 is 1 minus Z. It's atmospheric pressure going out, so it's just 1 over 1 atm. But that total N, this total N right here, I have to work with a little bit. So let me kind of tuck it in right here. Is the total N, is that the number of moles of CO2 plus the number of moles of CO plus the number of moles of O2 plus the number of moles of H2O plus the number of moles of N2? Does it account for the N2 and H2O in our products? It does. And they are considered inert. So if you see the word inert, that means they're just not participating in this reaction. They're not dissociating, but they're interfering with it, and so they come into play. So what happens is this is, if I write it out, this is 1 minus Z, this is Z, this is Z over 2, this is 2, that looks like a Z, but it's a 2, and this is 7.52. So when you sum it all up, N is, let me write it here, 10.52 plus Z over 2. That's what total N is. You okay with that? It's like this 1 minus Z cancels with that 1 minus Z, so I have a 1 plus a 2 plus a 7.52. That gives me the 10.52. And then I have a Z over 2 left over as well. And now I raise it to the power 1/2. That equation depends on the temperature. Temperature was given, you went to the table, you got the K, you got this equation, you said one equation, one unknown, let's solve for Z, and I'll get my equilibrium composition. But we don't know the temperature. So to get the temperature, we have to go back to the previous chapter and do the energy balance. For an adiabatic reactor, oh, that term's 0, is equal to the sum over all the products of the stoichiometric coefficient times H bar minus the sum over all the reactants, the stoichiometric coefficient H bar. How many people remember that? 0 is equal to, yeah, does it look familiar? It's our energy balance. Don't forget, 2 balances, one associated with chemical equilibrium, one associated with energy, first law. Now we're going to this first law. This equation looks like 0 is equal to, let me write it out, okay? The number of moles times, let me kind of write it out like this. The number times the enthalpy of formation plus the enthalpy at the equilibrium flame temperature minus the enthalpy at the reference 298 temperature. All of that for each product. First product would be CO2. Then you would do the same thing. You would say N times the enthalpy of formation plus the enthalpy at the unknown equilibrium flame temperature, that's the product exiting temperature, minus H bar T ref. And that's all for the second product, which is CO. Then I have to do N times H bar equilibrium flame minus H T ref, close parenthesis. What's our second? It's not CO, it's O2 plus, hey, we didn't even get through the whole list of our products, did we? The same thing for our H2O plus the same thing for our N2. Now we finally get to the minus for the reactants. For our reactants, we had N times the enthalpy formation minus the enthalpy of the incoming minus the enthalpy of the reference temperature. Bar, bar, bar. Put a bracket and a bracket. And the first reactant is CH4. And then we have minus NO2 minus N2. Both of these are reactants. Does all that make sense? I didn't write it all down, but does it make sense? A lot of these terms are zero, like the enthalpy formation of nitrogen is zero, the enthalpy formation of oxygen zero, the delta H, the N and the reference are the same temperature, 298. For methane, that delta H is zero. The enthalpy of formation of methane is not zero. So that's really the only term. But what is that coefficient in front of for the methane? 1. The coefficient in our equation is just 1 coming from right here. Okay, let's come up here to O2. Enthalpy of formation of O2 is 0, but this is not 0 because we don't know that the equilibrium temperature. And the same for the H2O, same for the nitrogen. This is now almost beyond tedious. So when you get to tedious, you jump to Excel. Can I solve it the rest of the way in Excel? Okay, let's do that. So we come to Excel. I like to just start and say, I'm trying to look for the equilibrium flame temperature in Kelvin. And I anticipate having to iterate. It may be 2000 degrees Kelvin. It may be 1800 Kelvin. That is where I'm going to finally get the solution, but I'm going to have to iterate to get it. You'd have to iterate by hand. Let Excel do the iteration for you. Also, Z was an unknown determining value. Maybe it's 0.1. What was Z again? It was the amount of the CO that dissociated. True? So it's not going to be above 1. But maybe it's 5%. Maybe it's 0.05. Maybe it's 12%, 0.12. Whoops, 0.12. But it's some value. So those two, and I like to color code them so that I know those two are things I'm going to iterate. To solve first for the chemical equation, the chemical equilibrium equation, I'm going to need to get K. I'm going to need to get K as a function of temperature. True? I remember my table, so I want Excel to be able to do that for different values of K. If I put in 1800 in that cell, or 1900 in that cell, or 2000 in that cell, I want it to automatically get the K for me. That means I really have to get the data out of the table, copy it, type it in and copy it, and get it into Excel somewhere. And so I'm just going to put it in the same sheet over here to the side. And so this is for the CO2 dissociation. You can check it. The temperature's here in Kelvin, and this is the log base 10 of K. It starts large negative and gets larger as we go along, okay? Well, to do that, what I'm going to do is I'm going to get the log base 10 of K right here. It's a function of that temperature. I use two calls. Maybe you're a pro at Excel. Maybe you know how to do this better than me, but I'm going to show you one way to do it. And the first thing you do is find a percent rank, and we're going to do it for inclusive. Now you can read more about this routine, but that's the routine. And since I'm coming in with temperature, I need to know where that 2000 falls in this range of temperatures. So in that given array, see the array, that's my array, I want to know where this value of x, 2000 or temperature, falls. And significance, you can read more about it by just clicking, but put it to be like 7 because it's the number of significant digits that it does the percent rank in, okay? So if I do that, 2000 is about 37% of the way through the data set. 500 is about 4% of the way through the data set. 298 is 0% of the way through the data set. And 3,500, what do you think 3,500 is going to be? Come on now, 100% of the way. Okay? So that's what you're doing. You're finding the percent of the way. The next thing is I want to take that value and get this one. Okay? Because these aren't in equal increments, are they? 298 to 500 is not an equal increment. It's not equal size steps. So it took me a while to figure out, do some Google searching. This percentile.inc, inclusive, right, of the array, this is the array that I want the value back out of, comma, given k, which is that input. And so if I get 3,500, it returns 0.19. Let me click over here some digits. 0.190. Let's check it. 3,500, 0.190. See that? Let's check the lower end, 298, and you get negative 45.066. Got it? Let's say it's 400. It's going to interpolate between these two. And so that's kind of helpful because we don't know the temperature, and it's not going to land perfectly on one of those lines in our table. So now we have that log base 10 of k. So now we want the equation, the equilibrium, chemical equilibrium equation, and we want that to be equal to 0. But it's a function of this k, so it's a function 10 to the exponent of that power. That's now k, right? Because I had to 10 to the power of that coefficient. Then minus, we wrote that equation out. What was that equation? It was z times square root of z divided by 2 divided by 1 minus z. Then we multiply times the pressure, that was 1 over. Then in the numerator we had that funny 10.52 plus z divided by 2, close parenthesis, that's 1 over that, close parenthesis, I could put right here to 0.5, or I could just come back here, come back here and take the square root of it right here, SQRT, square root, right? But there it is. So if the equilibrium flame temperature was 2000, this would be the log base 10 of that equilibrium constant. It would not be balanced because this z doesn't satisfy that equation. If I want to find the z that makes the chemical equilibrium equation balanced, I would go under Data tab right here, go under What If Analysis, go under Goal Seek, and say this cell C4, it's given this dancing box right here, I want to set that value to 0 by changing this value right here, and it'll iterate it, and that Excel says that's close enough to 0. Sometimes I don't like that. I say that's not 0. So I take 1,000, oops, and multiply everything. And then I drive that to 0 again. What if, goal seek, set that to 0. What cell again? Oops, I need to get that cell, C4, not C5, right? Set it to 0 by changing cell C2. And there you go. See what I did? It's like Newton-Raphson's root finding. All right, now that's half of the problem because we don't know the equilibrium flame temperature. It could be 2100. And if it is 2100, then I got to go rebalance for the chemical equilibrium. Now we've done the energy before. So as you might think, I solved this problem before coming into class. I'm going to go to a sheet and grab it, but it's parts that you've seen already, or I've tried to show in lecture if you were in the lecture. So if I come over here and I grab this without you looking at too much, and I copy and I run back before you look at too much, and then I paste it, now I can explain it. So what do we have for an N? It's methane, oxygen, nitrogen. Those are the coefficients on the N, true? What about the outs? CO2, CO, O2, blah, blah, blah. The CO, it's 1 minus Z is what's coming out. So it depends on what is in the cell C2. And likewise, it's Z for the amount of CO coming out. And it's Z over 2. But 2 is 2 for the H2O coming out, and 7.52 is that going out, right? If you sum them up, we'll do that later. But you use the enthalpy of formations. You have to type those in by hand. And then this temperature right here is brought down from the temperature up here. So if this changes to 2200, everything in the blue gets updated in the energy calculation, because it calculates the enthalpy for the CO2 as a gas as a function of that temperature, enthalpy of CO, enthalpy, blah, blah, blah. So the sum happens over here where you have the product N times the enthalpy of formation plus enthalpy in minus enthalpy ref, which I just left blank because they're both at 298. And so this is the only on the sum on all of the reactants coming in. The products, though, you do have to have the enthalpy exiting, and that's different than enthalpy reference. You have the enthalpy formation, then you have the coefficient N in our equation. And then when you sum them all up, you get this term, true? So what we want is we want to have something like this. Equation for thermal or energy equation, where this was the chemical, CH or C for chemical equilibrium. This is thermal equilibrium, okay? So that would be the sum of the products minus the sum of the reactants. That term should be 0. It's a function both of T and Z, but it's primarily a function of T. Let's do what if analysis, goal seek. Take that cell that's dancing, set it equal to 0 or drive it to 0 by changing this temperature. So it says, okay, it's closer to 2307, but my chemistry is now in equilibrium, is it? So I come back and I say goal seek, and I say drive that value to 0 by changing this. And then the energy is not in balance. So you do goal seek, drive it to 0 by changing the temperature. And it goes back and forth, back and forth. But there's another routine, so I get a total error. So the equation, EQC, I'm going to square it. Then I'm going to add to it EQT, quantity squared. Does that make sense? And so it's like this is equal to this amount squared plus this amount squared. All right. It's a pretty big number. Let me try and make it look a little prettier. All right. And you can see that if I drive this one to 0 data, what if, goal seek, set the value to 0 by changing Z, okay, that it upsets the energy balance, and then this number is no longer close to 0. But I'm going to do this, what if, goal seek, to the value 0 by changing the temperature. Somehow it looks like we're getting close to a balance equation, but at this point you can come over to solver. I don't know why they have goal seeking here under what if analysis and solver over here, but you sometimes have to do the add-in for solver separately. So once you get this open, you can say I want to take the cell C19, that's my objective. I want to minimize it or maximize it or make it a value of this. Minimize it by changing, and the key is by changing variable cells as a plural. I can change both of those. It'll start to change both of those to try to drive that one cell to 0 or minimize it. So good luck, because it's nonlinear. Sometimes it works. If you have a good starting point in numerical methods class, a lot of times your algorithms will converge. You have a way off starting point, nonlinear root finding team, it won't converge. Let's see if it'll converge. Solver found all constraints are satisfied. Well, let's do this. Let's change this value to 2250 and 0.105. All right. Now let's see if it'll do a solve. See nothing, solve. Okay, that looks pretty good. Okay, now I could play with it a little bit. I look at this value. I want that to be 0. I already boosted its magnitude by 1,000, right? I look at this value. Oops. Yeah, that value. That's pretty good. Negative 0.5. Remember all these big numbers over here? So the energy balance is pretty good. The equilibrium balance looks like it's pretty good. So this is pretty good. I wouldn't trust that many digits, of course not. So we'll clean it up a little bit, maybe that much, and come over here. Something like that. Or that's good to 3 digits. This is way too many still. So that's how many Kelvin? Temperature? 2262. I wouldn't even trust it to that. I'd say 2260, 2260, something like that. And then, you know, it's sensitive, so maybe I should go back, leave it alone, because now that's 0. But there's your solution for the temperature, the final outlet equilibrium temperature. You can even box it. What about the fractions? You can just put your answer over here, y, where y is the amount of CO2 divided by the sum. Put that $, drag this down for all of them. Make sure the sum goes to 1. Just to double check, it does. Maybe I want to put those as percentages, and so I can read it. So the nitrogen in the product, 71.1% is nitrogen. 18.9% is water. 0.5% is oxygen. About 1% is carbon monoxide, and 8.5% is carbon dioxide. So there's your other part B. True. So that's how you solve this problem in Excel.